Good day everyone, my name is Panganiban, together with my co-author VALEROS and our thesis advisor Dr. Jeremiah Miliare, and I'm going to discuss our research entitled Preparation and Characterization of Nanozeolite Modified High-Impact Polystyrene via Casting Method. In recent years, with the rapid development of industrial activities such as leather and tanning, paint and dye manufacturing, paper and pulp production, cosmetics, textile industry, rubber processing, and reusing sustainable resources such as water and materials have generated wastewater containing dyes and unleashed a public health crisis. Water pollution has exacerbated the water crisis, causing severe damage to the global economy, resulting in the integration of social or worldwide conflicts, and the disturbance of industrial operations and supply chains. Dyes are known to be naturally toxic and carcinogenic, with disadvantageous consequences on humans, animals, and plants living in the environment. To overcome environmental problems caused by dyes, developing low-cost technologies and materials to remove these colored effluents prior to major contamination has caught our attention. Membranes have become increasingly popular in recent years for a wide range of applications, particularly in the field of water in wastewater treatment, as well as declamation of effluents from various sources. Membrane technology is ascendable and modular. It is also eco-friendly, low maintenance, and capable of high purification standards. It is more effective than other treatments in terms of efficiency. One of these is nanofiltration, in which it is one of remediation technologies in the removal of organic and inorganic pollutants from wastewater. And also, according to the study of Brugan et al., the most promising and powerful tool for separating organic dye molecules and inorganic salts is water purification via membrane separation in nanofiltration technologies. Also, several studies have used polymer nanocomposite using polysulfone, polyethyramide, and polyaniline-based nanocomposites with reinforcing nanoparticles and non-solvents. A polymer that hasn't been used as a polymer matrix in the removal of dyes in wastewater is high-impact polystyrene or HIPS, and that is why we have come up using HIPS as our polymers. So first, I'll introduce you to the properties of high-impact polystyrene or HIPS. HIPS has high tensile strength, high impact resistance, and is very light. HIPS polymer has multi-phase systems with polybutadiene disseminated in a rigid polystyrene matrix and has improved fracture resistance. It is known as strengthened polystyrene and a strong alternative to the highly brittle and rigid polystyrene. HIPS is a thermoplastic resin produced by a polymerizing polybutadiene elastomer and polystyrene monomer, and it combines many of the positive effects of plastics and rubber, including odorless, tastelessness, excellent dimensional stability, and high mechanical strength. So polymers can be improved by adding fillers, and one of the most promising filler materials for improving dye removal in wastewater is nanozeolite. Nanozeolites have been discovered to be more efficient in wastewater treatment than micro-sized zeolites. This is because nanozeolites have a higher surface area and a surface active sites, as well as the ability to be reused. Due to the increasing problem in aqueous solutions, some researchers investigate the removal of heavy metals and dyes with the use of nanozeolite. In this research study, the goal is to produce a particulate reinforced composite membrane using HIPS as the polymer matrix and nanozeolite as the potential filler for the dye removal. This research looks at surface roughness, porosity, chemical functional groups, and hydrophilicity of the membranes. This study does not cover the actual experimentation on dye removal from water. Also, to determine the presence of certain functional groups using Fourier transform infrared spectroscopy or FTIR, to check the morphology of the membranes using scanning electron microscopy or SEM, and to use contact angle goniometer to check the hydrophilicity. For the methodology, the materials and chemicals were purchased from Chembra's Products Solutions, Sigma Aldrich, and the Department of Science and Technology Material Science Division. Membranes were prepared from homogeneous polymeric solutions of HIPS and nanozeolite in NMP by the non-solvent-induced phase separation methods or NIPS. HIPS NMP solutions have a 20-80 weight% composition with various nanozeolite concentrations, which is 0.25%, 0.5%, and 0.75%. At room temperature, these polymeric solutions were casted onto non-woven supports using a 30-meter casting knife and submerged in a coagulation bath to complete the phase separation and the form of the membranes. This image shows the morphology of the membrane. It is clear that the increase in nanozeolite's filler leads to a decrease in porosity of the membranes. Also, it can be suggested that the solution properties changed considerably as nanozeolite particles were added, and that is the high rate of evaporation of solvents in pure HIPS goes to a minimum, especially at 0.5 and 0.75% weight of nanozeolite addition. The reason can be due to the entrapment of solvent molecules into the porous structure of nanozeolite particles, which limits their escape during the solidification stage of NIPS process. This allows the HIPS molecules to assemble and form a finer surface for the nanocomposite membranes. The decrease in porosity is not helpful in general if we want to increase the permeability of wastewater in membrane. However, lower nanozeolite amount may have a gradual effect on the porous nature of HIPS, which can be used to control the size of the pores, particularly in the nano level, which is the requirement for dye removal. This figure is the FTIR spectra of HIPS nanozeolite with varying concentrations membranes. The peaks located at 3025.72 are attributed to the CH stretching of alkaline group of butadiene. Due to the addition of polybutadiene, high-impact polystyrene exhibited improved strength qualities when compared to pure polystyrene. Different absorption peaks can be used to show the presence of polybutadiene. When nanozeolite was added to HIPS, the broad transmittance peak at 3400 has decreased, especially for the 0.25% and 0.75% samples. This can be due to the entrapment of water to the crevices of nanozeolite, dispersing the water molecules, which change the response to infrared light. The small peaks at around 1700 and a broader one at 2100 also began to change at higher nanozeolite content, suggesting for conjugation of carbon-carbon bonds. Shoulder peaking at around 1600, also from carbon-carbon configurational changes of the butadiene component as a result of nanozeolite interaction, can also be observed. Then at 800 to 850, the presence of nanozeolite may have contributed to internal vibrations of silicon oxide and aluminum oxide, which were more pronounced at 0.25 and 0.75% nanozeolite content. The last characterization technique that we've performed is contact angle goniometer. Contact angle is one of the common ways to measure the wettability of a surface or material. As we can see, the pure sample has a contact angle of 97.11 degrees, which means that the pure sample is hydrophobic. However, upon the addition of nanozeolite particle, it can be observed that the contact angle decreases. The sample became hydrophilic when there were 0.50% and 0.75% nanozeolite added to the sample. This is because nanozeolite have a very high potential for suction and absorption of water due to its porous structure and the polar species present within the structure of zeolite. This means that upon adding nanozeolite, the hydrophilicity of the membrane increases. The hydrophilicity of the membrane is very important for dye removal, as it is often the case that the carrier solvent is water. This means that the nanozeolite is a good additive for a hydrophobic polymer like HIPs, especially for use in filtration of dyes. The silica component of nanozeolite complements with the hydrophobic HIPs, while also having a hydrophilic component due to the alumina of nanozeolite. However, if it's true that agglomeration may occur at 0.75% nanozeolite, a value of 85.05 degree contact angle will not be enough for a free-flowing dye solution in the nanocomposite membrane. Thus, finding ways to prevent agglomeration would be beneficial to minimize the hydrophilic effect of nanozeolite to the HIPS polymer. So for the conclusion, nanocomposite with HIPS and nanozeolite has been successfully fabricated using NIPS. As nanozeolite is absorbed into the polymer, FTIR peak patterns of the produced membranes reveal a probable filler matrix interaction. SEM result shows that the porosity of pure HIPS decreases as we add nanozeolite. This can be due to the slower rate of evaporation due to the trapping of the solvent into the porous structure of the nanozeolite particles. Nanozeolite helps for the entrapment of solvent molecules, so HIPS can have time to assemble because of the gradual evaporation of the solvent. SEM also implies a possible agglomeration at 0.75% nanozeolite added as they get intact with each other, forming some porous areas on the surface. Contact angle shows that as we add nanozeolite, the contact angle decreases, making the nanocomposite hydrophilic. Because of its porous nature and the presence of polar species within the zeolite structure, nanozeolite has a significant potential for water suction and absorption. The results of the characterization of the nanocomposite shows that the hydrophilic property improves as nanozeolite is added. However, different ways of dispersing the nanoparticles are needed, as this may even allow smaller amounts of nanozeolite to cause a controlled effect on the porosity while still exhibiting a hydrophilic character. And that is all for our paper entitled Preparation and Characterization of Nanozeolite Modified High-Impact Polystyrene via Casting Method. Thank you for listening and have a good day.